Okay, so now we're going to talk about section 3.3, which has to do with increasing and decreasing functions, and more specifically related to data science and the gradient descent method that we discussed in a previous lecture. We're going to formalize why we can do such an algorithm to find local extrema. Okay, so let's start with the following picture. So x and y, and then suppose our function looks like this. Okay, so as x is increasing here, right? So if we pick any two x over here, we see that, so this is like x1 and this is like x2. This would be f at x1, and this would be f at x2, right? So we see in this picture here that f of x1 is greater than f of x2. But here, x1 is less than x2. So on this interval over here, we'd say that the function is decreasing. All right there. Right, as we increase our x, the values for the function evaluated at the x is going down. Here, we'd say that this is constant over this interval here, because the value for any x that you pick on that interval is going to be the same. And then here, let's say we pick like x3 and x4. We see that as x increases, the function evaluated at that value also increases. So we'd say over here that we're increasing. Okay. Now to state that formally, let me write down this definition. So definition. So a function f is increasing on an interval when x1 less than x2 implies f at x1 is less than f at x2. Okay. So, and then also function f is decreasing on an interval when x1 less than x2 implies f of x2 is less than f of x1. Now, there's actually a typo in your textbook that I found where the definition, they don't change it for some reason. It's just a typo, but this is the actual definition. Okay, so just to go back to the picture, increasing, so if we have x1 less than x2, then f of x1 is less than f of x2. So over here, this is like x3 is less than x4, right? But then the function's values here are smaller than the function's values here. Okay? So that'd be increasing. For decreasing, if x1 is less than x2, then f of x1 is greater than f of x2. So that'd be decreasing, which is right here. Okay? So hopefully that's straightforward. Now, I'm going to have to erase that eventually, but I'm going to write down a theorem and then give the argument over there. So theorem, I think this is labeled 3.5. So let f be continuous on the closed interval AB and differentiable on the open interval AB. Okay. So there's three parts, this theorem. Part one, if f prime of x is greater than 0, all x in the open interval AB, then f is increasing on that interval AB. Part two, if f prime of x is less than 0, for all x in AB, then f is decreasing on AB. And then finally, part three, if f prime of x is equal to 0 for all x in the open interval AB, then f is constant on that interval. Oh, these are all closed intervals. Yeah, as soon as I saw the constant part, I was like, oh, wait a minute, there's no, we can actually extend this to the full closed interval instead of just the open. Okay. So this is actually why we can use gradient descent, this theorem, because this tells us that the sign of the derivative over a given interval tells us whether or not if we go right or left, if we're going up or down, right? So if we know the derivative at a point is greater than 0 and it's for a little interval around that point, then we know that as x increases, the function f increases. So gradient descent, we always want to go down. So if it's positive over some little interval, the derivative that is, then we don't want to go to the right, we want to decrease x in order to decrease the function. And the same thing can be said for the derivative being less than 0 on a given interval. That means that on that interval, as x increases, f decreases, right? So we want to continue that direction. Okay. So let's look at the proof of this. So we'll just look at the proof of part 1 of this theorem. And the proof of part 1 is basically the same as the proof of part 2, and part 3 is what we already know. So proving just part 1 is sufficient to argue why this theorem is true. So we're going to assume for part 1 that the derivative is greater than or equal to 0 for all x in some closed interval AB. And I messed it up again. I apologize. My intuition was correct the first time. For x in that open interval, then it's increasing in the closed interval. And then if the derivative is less than 0 for x on the open interval, then f is decreasing on the closed interval. So I apologize for that. So we're going to assume f prime of x for part 1 there is greater than 0 for all x in the closed interval AB. Open interval AB. And we want to show that the function f is increasing. So in order to do that, we just need to pick some x1 less than x2 in there and then show that f has to be increasing on this interval. So we say next, let x1 be strictly less than x2 for some choice of x1 and x2 in the open interval AB. Okay. So what's happening here is that we have some closed interval AB, and then we're looking inside of AB, and we just pick x1 less than x2, right? So we don't know what the function looks like in there. We just know that the function is continuous and differentiable everywhere in there, right? So what we're going to use is the mean value theorem to get that there's some c inside there. So we can say by the mean value theorem, there is c with x1 less than c, which is less than x2, so that f prime at c is equal to f at x2 minus f at x1 all over x2 minus x1. Right, the function f is continuous and differentiable in the same way that we stated for the hypothesis of the mean value theorem. So we can just treat x1 and x2 as like the endpoints of our interval. We know that f is continuous over that closed interval and differentiable over the open interval. So we know that there's some c in there, that the derivative at c is equal to the slope between the points x1 comma f of x1 and x2 comma f of x2. That's what that's saying. But we know that f prime of x is greater than 0 for all x and everywhere in that interval. So we know that this is greater than 0 for, we know that this derivative is greater than 0. So we can say maybe like hence maybe that is greater than 0. Multiply both sides by x2 minus x1, and you get that since that's greater than that, the sign of the inequality does not change, right? That's a positive number, so you multiply both sides by that positive number. It's still greater than 0, so then we get that, maybe that f of x2 minus f of x1 is greater than 0, which means that f of x2 is greater than f of x1. And that finishes the proof of part 1. Why? Because we just picked arbitrary x1 and x2 in there with x1 less than x2. And then we apply the mean value theorem and get that the derivative at some point c is equal to the slope between those points. Under this assumption, it's greater than 0, which means that if we evaluate this in terms of just the f's and multiply both sides by the denominator, we get that this happens. So if we pick any x1 and x2 that satisfies that, we get this, which means that the function is indeed increasing over that interval, which proves that part. Now, a similar method can be adapted from that proof to prove part 2, and part 3 is kind of straightforward. So let's see if we can use this information about the derivative to tell us about the behavior of a function that we don't really know what it looks like. Or we can pretend we don't know what it looks like. So find the open intervals on which the function f of x equals to x cubed minus 3 over 2 x squared is increasing or decreasing. Okay, I'm going to pause the video now and let all of you kind of work on this problem. Okay, so let's figure it out. So we're going to use this theorem to give us insight about the behavior of this function. And in order to use this theorem, we definitely need to take the first derivative. So f prime of x is going to be 3x squared minus 3x, which is equal to 3x times x minus 1, right? So this derivative exists everywhere. So we know the critical points of this function are only going to occur when the derivative is equal to 0. There are no points where the derivative doesn't exist. So where does this equal to 0? So the critical numbers are, so are when x is equal to 0 and when x is equal to 1. So we know the behavior of this thing, right? It's achieving some type of local min, local max, or maybe like constant somewhere around these values here, right? So what we can do is we can say, let's break up the real line into intervals. So the intervals in question that we need to consider whether or not this function is increasing, decreasing, or constant are going to be to the left of that, in between these two, and to the right of this value. So we need to look at negative infinity to 0. We need to look at 0 to 1. And we need to look at 1 to infinity. Okay? So we just have to pick a number in there, a number in there, a number in there. Test the sign of the derivative for that given number that we pick. And that should tell us something about the behavior of the function on these intervals. So let's consider this first one. Let's take x is equal to -1. So then f prime at -1 is equal to -3 times -2 is +6, which is greater than 0, which we can say this implies f increasing on negative infinity to 0. You pick any point over here, you'll see that the derivative is going to be positive, which according to this theorem says that f is increasing on that interval over here. If we take x in this second interval, maybe like a half, then f prime of 1/2 is going to be, so 3/2 times -1/2. That'll be -3/4, which is less than 0, which implies f is decreasing on that interval there. So if you take any number in there, you'll see that it's negative. So it would be decreasing on 0, 1. Because the derivative is negative on that interval, which according to theorem 3.5 says that the function is decreasing there. Okay, so now let's pick an x over there. So we pick x to be like 2, maybe. Then f prime of 2 is equal to 6 times 1, so which is just 6, which is greater than 0, which implies that f is increasing on 1 to infinity. Okay? So with that being said, we see that the function is changing from increasing to decreasing when x is equal to 0. We see that the function is changing from decreasing to increasing at x is equal to 1. So let me pose a question. The question is 0, comma f of 0 for that function there, a local maximum or a local minimum. So if we break this function up until on this interval, and this interval, we know it's increasing there and decreasing there. So what does that mean about this critical number and the function evaluated at that critical number? We know it's going to be an extrema, but what type of extrema is it? Is it maximum or minimum? Anybody want to answer?
So maximum?
Right. So here's like our interval, right? Here's 0, here's 1. We know on negative infinity to 0, the function is increasing. So it's like going up, right? And then at that point, wherever it's at, it then starts to decrease. So we know that this is going to be a maximum. What about the point 1 comma f of 1? Is that minimum or maximum?
So minimum?
It's a minimum, right? Because we know on this interval here, we're going down, right? But then on 1 to infinity, we know that f is increasing. So we're going up, which means that we're bottoming out somewhere. So this would be a local min. So this is what's often referred to as the first derivative test. So I'm just going to say it out loud instead of writing it. If the derivative at a critical point to the left starts off negative and then becomes positive after that critical point, then we know we're at a local minimum. If the derivative is positive and then goes negative after the critical point, then we're at a local maximum. If the derivative does not change signs, then we're at neither. So maybe I can just like draw a picture to describe this thing called the first derivative test. It's stated as a theorem in your textbook, but I think that stating it as a theorem takes away from using the derivative as a tool. If you just remember that the theorem, it doesn't tell you, it doesn't reinforce what the derivative is telling you. Actually thinking for a moment and figuring it out on your own, I think that reinforces how to use a derivative as a tool. So if we have some function like that, right, we know, like here's C, we know that we're decreasing here by just checking the derivative for each point over there. And then, so this would be, so this way, we know the function is decreasing. Since f prime of x is less than 0, for x anywhere like this, suppose, for some x less than c, we know that as we get close to c that we're decreasing. Whereas like over here, we're increasing because f prime of x is greater than 0 for x greater than c. And when I'm using 4x greater than c and 4x less than c, I mean and x close to c. Because look over there, it actually is increasing right there. But if we choose any x like close to it, we know that we're decreasing. Just like over here, we choose x close to c, we know that we're increasing even though it looks like it's decreasing over there. So again, and for x close c. Okay. you can look up the theorem in the textbook, but more or less, the theorem is just stating what you can observe by drawing a picture and reminding yourself of what's happening. As the slope of the tangent line is negative, if the slope of the tangent line then becomes positive, you have to be at a minimum. If the slope of the tangent line at a point is positive, and then on the other side it becomes negative, you know that you have to be at a local maximum. It's that simple. Okay. So for this section, 3.3 homework. 5 through 9, and then 11 through 37 odd. And again, this is going to be due 3. What was it? 29. So next Monday. Okay, so I more or less ran out of time. So I'm going to pause the video now or stop the video.